Hi, this is day 2 of the 30 days challenge. Today I'm going to talk about the heap data structure. Heap data structure is a complete binary tree which satisfies the heap property. So a heap is of two types, max heap and a min heap. For a max heap, the heap property says that any given node should be greater than or equal to its descendants. So if we take the node 12, then this node should be greater than its children. Or if we take this node 10, then it should be greater than its children, or it can be equal also. We can have duplicates as well. And that is the heap property of a max heap. For a min heap, the heap property says that any given node should be lesser than or equal to its children. So this is an example of a min heap. To understand the concept of heap sort and priority queues, we need to understand how we can represent binary trees in the form of an array. Let's take any node I. Let's take a node 12. Its index is 1. So I is equal to 1. If we want to know where its left child is, the left child is at 2i plus 1. 2i plus 1. So in this case, it will be 3. As you can see, it's the index of the left child of this node is 3. And if you want to know where the right child of an index of any node in the array, we can compute that with 2i plus 2. That is 4. So we have taken this node 12, its index is I. So its right child will be at index 4. And this is its left child, this is the right child. So its right child is index 4. That's how you can represent it in an array. Or if you don't want to compute it using these formulas every time, just fill it level by level and from left to right. So 1, then 2 and 9, then 5, 6, 10. That's how we represent binary trees in the form of arrays. Learn about heaps. We can either see the insertion and deletion on max or min heap. It will be the same for the other one. So today I will be using the max heap. Visual algo. Here you can visualize the algorithms or data structures. So I will be explaining the insertion. There are two operations that we can perform on heaps, that is insertion and deletion. So first, let's see the insertion in the max heap. We're using these elements 50, 30, 20. If you go to this right here, you can enter what all numbers you want to use. 50, 30, 20, 30, 20, 15, 10, 8, and 16. Just click on go. A heap will get created. As you can see, the heap got created from level by level and it filled from left to right. We want to see how the insertion works. You can minimize the speed. Let's try to insert. And this heap is also represented in the form of an array here. 50 is the first level, that is 50. On the second level, we have 30 and 20, to 30 and 20. On the next level, we have 15, 10, 8, 16. 15, 10, 8, and 16. Now I want to insert 60 to the heap. Right, 60 here. So how the insertion works is, know that in a max heap, the greatest element should be at the root. That is, the root element should be the greatest of all its children. So if I, but we don't directly insert it here. We always insert into the heap at the first available space. Means, if you see this heap, uh, in this the available space is here. This is where we can insert the new node. Here, if you see, this is zero index, this is zero, 1, 2, 3, 4, 5, 6, 7. So 7 at the seventh position, we can, it's a, in the array is based on index 1, so it will be 8, 1, 2, 3, 4, 5, 6, 7, 8. So the 8th position will be here on the left, and we also want to maintain the complete binary tree property while we are inserting. So that's how we insert into the complete binary tree also. So if I just go, that's where the 60 is inserted, right? 60 is inserted at the last position. Then it is compared with its parent. If the parent is smaller, then we need to swap it. Again, that is compared with its parent. If it is smaller, then swap it. Again, compare with the parent. If the parent is smaller, swap it until we reach the node root. That's how it's done. And if you see it here, that's how it will be. First, when we insert, it's inserted at the last position. Then after swapping, that is how the final heap looks like in the form of an array. So the time that it takes to insert and swap and then maintain the heap property is big of log n, because it depends on the number of swaps that we make and also the height. As if the height is smaller, then it will take less time. If the height is larger, then it will take more time. So it depends on the height, and the height of a complete binary tree is max big of log n, because we cannot have subtrees which are, one subtree cannot be larger than the other, because we need to fill one level completely before we insert into the next level. So that's how the uh, maximum height of a complete binary tree is always log n. And while inserting, if suppose the node that we are inserting is the smallest, then there will be no need of any swaps, so that will be big of 1. But if it's the largest node that we insert, then it will take big of log n. So the worst case is big of log n. Similarly, let's see the deletion in a max heap. You cannot delete any other element but the root. Means in a max heap or in a min heap, if you want to delete any element, you should delete the root only, and then you should adjust the binary tree or the complete binary tree or heap to maintain its heap property. Since we are using the max heap property here, let's go and create a max heap of the same numbers. 20. This is the creation of the heap. This I will talk about in the next session while talking about heap sort. So this is the heap that we have. This is the max heap that we have. I'm talking about deletion in a max heap. So here extract max is there. We can delete the root node from the max heap. So if you click on extract max and just say once, we took out that root node and yeah, so this is the important point. After deleting the root node, you should swap that root node with the last element in the heap. Suppose we want to delete 50 here. So remove 50 from the heap and in place of that put the last element from the heap. So in the array it's easier to see. The last element is 16. So place 16 in that empty space. After that, yeah, once you do that, compare this root node with its children. No, compare the children of this node, 30 and 20, whichever is greater, since it's a max seed, whichever is greater, compare that with the root. And if root is smaller, then swap. Again, we are here. That's it. 16 came here, then we swapped it. After that, here also, after you come here, compare its children. Whichever is greater, 15. In this case, 15 is greater. Compare that with a node. Then it is greater in this case. So no need of any swaps. So after we delete the root, we need to replace the root node with the last element from the heap, and then we need to maintain and adjust its heap property. And to to maintain the heap property, what we are doing, we first compare the children among themselves. Whichever is greater, we compare that with the root, and if the root is smaller, then we need to swap it. Again, do the same with the child that we swapped with. Compare its children. If whichever is greater, compare that with the root. If the root is greater, then no need to um, log n because it depends on the number of swaps that we need to make and also on the height of the heap or binary tree. Another important observation is while inserting any node, suppose we want to insert 88 to this. What we are doing, we inserted it at the last position and then we are swapping it with its parent and then again we are comparing and swapping with its parent. So while insertion, we start from the bottom and we go up. So it's the bottom up approach. But while we are deleting, we start from the root and we go down. That's top down approach. That's it. Thanks.